talking about some applications of this CHSH rigidity theorem in terms of how we can use it to control untrusted quantum systems. This is this is joint work with Bob and with Umesh. So basically, we showed before that when you play lots of CHSH games in sequence, and the devices win enough of them, and this forces. The only way this is possible is if they share quite a lot of entanglement, and if they measure this entanglement in a very nice way. But that's not so interesting. In particular, you know, when you're done playing the games, they've used up all the entanglement that you showed they had. So the games destroy the entanglement just as much as they show that you have it. So today I just want to show you how this kind of theorem is actually still useful, even though it seems like it's destroying the entanglement. And how we can use this kind of theorem to force these quantum devices to actually do whatever we want. So prepare arbitrary quantum states as long as we can efficiently prepare them, or full quantum computation. So the model I want to talk about is delegated computation, which we heard about yesterday. It's this cryptographic idea that you have some weak device, like a cell phone or some computationally weak device, and there's some powerful server, and the cell phone wants to outsource some computation to the server, a known computation to the server. So it's not like homomorphic encryption. And you want to guarantee primarily that the server's output is correct, even though you don't trust it to do something. So you need to somehow build in traps or checks or some way of making sure that it's doing the computation you ask it to. And second, a nice property is that the computation is secret. This is actually quite easy to achieve, for us at least. So the server doesn't actually know what you're doing, what he's doing to this data, except the most basic properties like the size of the circuit.
Isn't it a requirement for quantum computation in these?
Isn't it a requirement?
No, because otherwise you won't be able to guarantee that it's correct.
Which property?
If you can guarantee that it's correct, it has to be secret.
No, I mean, actually, maybe. The circuit itself is secret, not just the data is secret. So you could have a scheme where you tell the prover what the circuit is, and the data is somehow encrypted. So he doesn't learn the data, but you force him to apply the circuit. But yeah, something like this. So classically, you know, it's been studied for a long time, and a fair bit is known. Here's some brief results, but I'll skip over that. I'll just mention instead what we heard from Monday about sort of semi-quantum delegation. So I forget exactly what Joe called it. So the idea there was that you start with some quantum circuit that you're interested in, and you compile it into this protocol where you have one device that is able to create quantum states, simple quantum states, like 1 qubit quantum states, just like ket theta, where that's cosine theta comma sine theta. And he sends this quantum states over, or simple quantum states over to a fully quantum server, and there's traps and brickwork states and whatever, in order to make sure that the quantum prover applies some interesting quantum circuit. But this is not fully delegated quantum computation, because we still need the ability to prepare these quantum states, and that's quite helpful in the analyses. So today I really want to talk about fully delegated quantum computation, and unfortunately I don't know how to do it. I guess nobody knows how to do it with just one classical verifier and one quantum server. So what we'll do is we'll have 2 quantum servers, Alice and Bob, who are untrusted. They're entangled with each other potentially. Well, they'll have to be entangled if they want to win. But then everything else is fully classical. So the verifier is fully classical. All the messages to and from the provers are fully classical. And the idea is that, again, it's that you're going to run this big protocol. So the verifier is going to ask for all these tests to be played, and provided that there's a good probability of passing all these tests, the conclusion of the theorem is going to be that they applied the circuit you asked them to, and the result is correct. Yeah. So maybe before I try to explain how this works, let me try to ask why it's even a problem. So there's sort of an obvious approach here, and that may or might not work. So the obvious approach is just to take what we already know. So take this protocol that, take this semi-quantum or semi-classical delegated computation protocol, and then sort of split off half of it. So we need the verifier to prepare these 1-qubit quantum states. So let's just give that to Alice and let Bob play the role of the quantum server in this original protocol. And then so we ask Alice now to prepare these 1-qubit states. Now they share entanglements, so we can teleport them over to Bob, and then run the original protocol, right? So what's wrong with that? I mean, well, one simple thing is you have to make sure that Alice is sort of honest, like she's really creating and teleporting over to Bob the right 1-qubit states, the ones that you asked her to prepare. But that doesn't seem like it's a serious problem. I mean, you just in some random subset of the positions, you'll ask Bob to measure in the basis theta j plus pi over 2, and you make sure that he returns the right angle. Right? And that provides a check on Alice. So if she's preparing some state that's far away from ket theta j when you ask her to prepare it, then this measurement will catch it, should catch it. Right? And that should work because actually all these angles are uniformly distributed. I think they're like uniformly random multiples of pi over 8 in the scheme we saw Monday, something like that. So really. Bob should have no idea what angles are coming in. So if you ask him to measure in this basis, he has no idea what answer to give, and so he kind of has nothing better to do than he better be measuring and returning the answer. That should catch Alice.
Just for understanding, do you assume that Alice picks her own theta, or that the classical verifier tells Alice which theta to teleport?
I don't know. You can do whatever you want. Probably. Tell her to.
Because it sounds currently to me that you're.
So I should say this is an obvious protocol. This is the wrong protocol. I mean, I'm not going to try to analyze this protocol. So I don't know exactly how. You can figure out the details to make it work.
I'm just confused because different ones have different reasons why they're wrong.
So it can only send Alice instructions to prepare states.
If Alice chose them herself, then she could just, her and Bob could
you
agree
presumably want the verifier to give the randomness to Alice. Like he just sends like a random number from 1 to 8, and that tells Alice which of the 8 theta j states to prepare. Because otherwise, yeah, she could prepare some sort of. It wouldn't really be a random string, and she could coordinate that with Bob. Yeah. So that's sort of the idea of this kind of scheme, or you could do it with any sort of semi-quantum scheme, that you could try to break it up in this way and have Alice do the state preparation part and have Bob do the computation part. It seems reasonable, and maybe you need a few more tests than this. It seems reasonable you can make something like this work. Maybe. The problem is it's really hard to analyze this kind of scheme. I mean, so the first problem is maybe not so complicated. I don't know. Like it could be that Alice sends some other state, some psi j instead of theta j, and Bob doesn't exactly measure in the theta j plus pi over 2 bases, but he does something that's slightly different, and somehow they conspire so that their answers always seem like they always give the right answer, even though they're not quite doing the right computation. I don't know, but maybe you could analyze this and show that can't happen. But I think maybe a more interesting problem with this kind of argument is that the cheating strategies could be much more sophisticated than just sending the wrong quantum state. I mean, it could be that Alice doesn't even send qubits to Bob. It could be that they don't even share entangled e-bits. Maybe they share some other kind of entanglement. And I mean, maybe Alice isn't sending information in tensor product. She's just sending some large state. Maybe Bob's measurements aren't in tensor product. What he measures in the first on this first supposed qubit, the second supposed qubit, they overlap in some complicated way. It's very hard to try to analyze this kind of scheme when you have no control over exactly what they're doing. There's no idea. There's no notion of even of locality or anything.
You do have a bound on the classical information that is transferred because it has to go through the verifier. So if the verifier will know that there are at most two n bits transferred for these n qubits that should be teleported, and then if the verifier checks a subset, like ask the second prover to open a subset of the bits back, then it might be that you could use the amount of information that has to be transferred and see that there can't be any extra information transferred because it just doesn't fit.
You're trying to understand the quantum state, not the classical information that the verifier has. Eventually, you're interested in the quantum computation, not in the classical.
Exactly, and the verifier wants to make sure that that A did not send anything except the quantum states to B, so not the classical description. That's what you want to ensure.
What you're saying is just bounding the size of the state or the amount of information, but you actually want to know that it's this tensor bar of theta j's.
I don't want to know that. The thing is, all I want to know is that. No, all I want to know is that the blue circle down there, that he only gets these quantum states and possibly in different encoding, whatever. But he should, from the information that that the verifier sends, he would not get anything more about the encoding, about the angles, than the encoded quantum states. And if additional information is sent, that could be simulated by the other prover anyway on its own.
Yeah.
Let me say just one thing. I don't know how to prove that this approach does not work.
Yeah.
But because from the teleportation you always get random bits which Alice has to tell the verifier in order to verify anything, to verify the teleportation, whatever. Any protocol that I know enables Alice and Bob to decide on a shared random string and fool the verifier to anything. I'm not smart enough to build a protocol that would bypass.
No, it's you use normal teleportation protocol, and the classical bits need to go to Alice. So there's a limit on the comment.
So Alice and Bob can pre-arrange and say whatever they want that will satisfy the verifier if he needs to accept something.
No.
Well, anyway, I think. I think it's possible that this kind of scheme is secure. We don't know for sure. We don't have any counterexamples. Counterexamples would be like a cheating strategy that works would be very interesting, or also, of course, a different analysis would be very interesting. But I guess I just want to point out that without any understanding of what the Hilbert spaces of Alice and Bob are, or what the quantum state that they have is, it's really hard to try to push through some kind of analysis. And so this is really sort of the moral, is that this theorem that we showed before, that when you play lots of CHSH games, the only way of doing it, and successfully, is to have a tensor product structure. That really allows us to limit the ways that Alice and Bob can cheat in this kind of protocol, and then you can suddenly start to bootstrap this into, quite simply, into theorems like delegated quantum computation. So we are able to show this kind of result, but in a different approach, not via these semi-classical, semi-quantum protocols.
So you have to modify the protocol, and it's possible that there could be a rigidity theorem for the original protocol also. But
yeah, I mean, it's possible there could be lots of rigidity
use the rigidity theorem for CHSH, then that gives you the tensor product structure, which you then apply to that.
Exactly.
Yep.
Yeah. And let me also say that this kind of in a sense, it answers this problem that motivated a lot of this work, which was how do you characterize these two black box devices? You don't know anything about what's going on inside them. They could even be adversarial, and you want to characterize and understand what their quantum state is. And this kind of result lets us do that. Actually, it's more than just delegated quantum computation. So in delegated computation, it just says, I know that the mathematical result of the circuit that I asked. I know the result of the circuit that I got is the same as what it should have been mathematically. But actually, our theorem is saying something stronger. It's actually allowing us to characterize the internal quantum states of these quantum devices at every step of the protocol. And so it's really a physical statement, not just a mathematical statement, I guess. So sort of a classical delegated computation scheme, there'd be no hope of characterizing what's going on inside the server. It's just doing the computation in some way, and somehow you get the right answer. But here we really are characterizing what's going on inside the quantum server. And we can ask it not just to do a computation, we could ask it to prepare some interesting quantum state. And it would do so. I mean, I don't know what you would do with it, but it would have this quantum state in its memory.
Up to local isometry.
Up to a change of basis. Yeah. So there'd be some direction or something in which you could see that.
Right. So what you're really forcing is the entanglement.
Yeah, and so that's why I say that's why I say it's not clear how interesting it is to know that he is a quantum state, because it's up to a change basis. Right. But it's still somehow different from the classical picture, I think. All right, so a second theorem that comes out of this is that mathematically QMIP equals MIP star. So let me just say what this means. It means that if you start with a quantum multi-prover interactive proofs, so you have a set of quantum provers who are entangled and they're the bad guys, and you have this quantum verifier and quantum messages, and they exchange messages to decide some language. So that's QMIP. MIP star is the same, except again you have quantum provers, but the verifier is fully classical, which means that the messages are also classical, and they're entangled. So clearly, sort of any protocol of this form is also of that form. I mean, a classical verifier is a special case of a quantum verifier, and so mathematically that means MIP star is contained in QMIP. So the statement that we show is actually the other direction. QMIP is contained in MIP star. In other words, we show that starting with a protocol like this, you can simulate it with a protocol like this on the right. So starting with a quantum verifier, you can simulate it with a classical verifier. And the way our proof works actually is we add two provers, Alice and Bob, and Alice and Bob and the verifier together essentially run the delegated quantum computation protocol. So these two together are, I guess the verifier delegates this quantum circuit to Alice and Bob in order to run this protocol. That's the idea. And I don't know, it might or might not be necessary to add two provers. Maybe you can do it by reusing like R1 and R2. I don't know why I use P1 and P2, but we don't know for sure, so I just stated.
I have a question. If you prove that these things are the same, are the inputs not completely incomparable, right? I mean, the quantum input is just this state, right?
So these I mean, mathematically, these are just classical languages decidable by a protocol like this. Yeah, and the statement is always like, it's just standard completeness statements.
This is the language, right?
Yeah, exactly. Yeah. Yeah.
Can you explain what's the difficulty in using R1 and R2 to also simulate the quantum verifier?
I don't know that there is a particular difficulty. A lot of the problems that we face is writing down the theorems. So maybe if you wrote down the theorem carefully, then you'd probably be able to prove it. Like, there's no conceptual difficulty, I don't think. It's mostly you just have to be careful that all the quantum information is in the right spot at the right time, and doing it like this sort of allows you to isolate it more easily. Yeah.
So in the second case, you've got classical messages to the provers, but is there some sort of teleportation where that simulates the quantum messages on the left side?
Yeah, actually, so do I say something here? So actually, the quantum messages can all be passed by classical teleportation. So you don't need. I mean, all these quantum messages are passed by classical teleportation to Alice and Bob, where they compute on them. But
You just mean teleportation? It's classical teleportation.
sorry,
Okay.
teleportation. Right. Maybe another point as well is that the round complexity is not very good either. So there's this point of adding provers, which probably we can fix. I don't know. There's another problem, which is the round complexity is very bad, which I definitely do not know how to fix. So it's known that QMIP can be parallelized down to just 3 rounds of communication. So this way, this way, this way. Sorry, or the other way, whatever. But that's not known for MIP star, and the way our proof works, certainly it blows up the round complexity quite a lot, because you need some rounds of communication to simulate every single gate of this quantum circuit over here, and so the round complexity is going to be like the size of the quantum verifier circuit, something like that, polynomial in that anyway. And that's the best we know.
So that's in the simulation or in the protocol that you impose the rigidity, the round complexity. Where does it come from again?
Sorry, here
Yeah.
on the right. No, I'll show in a second. You'll see. In 2 seconds. Okay. So let me say something about how we prove this. The first ingredient is this theorem from before about understanding sequential CHSH games. So here we have these two provers, Alice and Bob. We send these random bits. We get back responses, and they should satisfy some simple predicate. And here's the optimal strategy when you play multiple games. So if you feed Alice an input 1, she should apply. Okay, so they should share an EPR pair for every game, first of all. And secondly, if you feed Alice an input 1, she should apply a pi over 8 to measure in the z basis and return the result. If you feed her a 0, she should measure in the x basis rotated by pi over 8. And Bob, what he does is on input 1, he measures on the x basis. On input 0, he measures on the z basis. This is the optimal strategy. And it wins every game with probably about cosine squared pi over 8, which is about 85%. And so what we mentioned last time is that if you start with an arbitrary strategy for playing n times n of these games sequentially, and if there's a high probability that they win the optimal fraction of these games, then if you stock them at the beginning of a random block of little n games, the state of the quantum system at that point is going to be n EPR pairs, and the strategy for the next little n games is going to be exactly the strategy in this picture. Well, approximately the strategy in this picture. And of course, when they play that, they destroy the entanglement, but that's okay. So that's the first ingredient, which gives us structure, and this is really the most important ingredient in the proof. Let me point out something that Umesh also mentioned on Monday, which is this EPR pair is really nice. It has this property that if you measure it in any basis, like the theta plus pi over 2 basis, if Alice measures it in that basis, it collapses Bob's side to the same state. That's true more generally as well. If you take n EPR pairs and you measure in any orthonormal basis, like psi x, whatever result Alice gets, Bob has the same state up to complex conjugation. So collapsing one half collapses the other half to the same thing. Here's a proof. I'll skip it. The second ingredient is computation by teleportation. So if you haven't seen this before, well, here it is. This is actually, it's the same as the standard teleportation circuit, except I put a Hadamard here. So standard teleportation would take an input, and you'd get out the output here with some polycorrection, or here with some polycorrection, which you can fix. But since I put a Hadamard here, it sort of feeds in. So psi comes in, you get psi here, you get h psi here. So you've teleported into a Hadamard gate for free. And it means that instead of applying Hadamard gates to your data, you just prepare these resource states and then teleport into these resource states, and then the computation happens in the teleportation. So here's another example. So I've prepared a 4-qubit resource state with 2 EPR pairs and a CNOT between them. I apply these Bell measurements, which is just my shorthand for this little circuit here. Apply Bell measurements to both of the data qubits, and what comes out is a CNOT applied to the data qubits. That's teleporting to a CNOT gate. So you can do it with whatever you want. No, a lot of different things. So here's another example, a more complicated example, and I've sort of compiled into all the gates of this circuit. I've compiled into resource states. Like this Hadamard becomes a Bell pair with the Hadamard in the second half. The CNOT is that 4-qubit resource state, and there's a bunch of Bell measurements that teleport into each step of the circuit. So the way we're going to use this is we're going to, all these EPR pairs, we're going to split half is going to be owned by Alice, half is going to be owned by Bob. All the Bell measurements, we're going to say Alice does the Bell measurements, and wait. Actually, that's wrong, sorry, start over. What we're going to do is we're going to ask Bob to prepare these states fully on his side, these resource states. We're going to ask Alice to apply the Bell measurements fully on her side, and then the wires between them we're going to do by another round of teleportation along the shared EPR states. So the picture is this now. This picture here implements the same circuit by teleportation, computation by teleportation. So it's the same CHSH. It looks like, all right, so they share these EPR pairs. So here we have ket 0 comes in because Bob is measuring the first qubit in the z basis. That collapses Alice's first qubit to ket 0. And then she does a Bell basis measurement, which moves it over to this qubit here on Bob's side. he teleports into a Hadamard gate, so the qubit moves around to here and so on. You can just sort of trace the data through the circuit and see that it's implementing this same picture here, but just sort of wraps back and forth between Alice and Bob.
So the point here is that Alice has a bunch of resource states for the different gates, but she doesn't know what order they're applied in. Just,
for blindness, yeah, that'll be how it is.
Some number of C0 gates and some number of Hadamard gates, but Bob knows what order they're in, but he doesn't know which gate is which. He knows that you gate 1 and then gate 2 and gate 3, but he doesn't know which is gate 1 and which is gate 2.
Yeah, really, you can think of it as So Bob owns these resources, or Bob's the guy who's tasked with creating these blue boxed resource states.
Oh, sorry, I got them.
And so when Bob, and actually the way it'll work, when Bob creates this resource state, because of this property of collapsing EPR pairs, it'll actually be created on Alice's side. So Bob will make a measurement on his side, like he'll make this 2-qubit measurement, and that'll collapse the corresponding qubits on Alice's side into the correct resource state. And so when Bob's done, if he's honest, he knows that Alice has all these resource states. And then these bell pair measurements, they sort of wire them up in the right way. So the data goes into the right quantum state, out of the quantum state, into and out. And actually the reason the round complexity is high is because this has to be done adaptively. Because it's a universal circuit. Yeah, exactly. Not in this picture, but yeah. Other questions? Okay. And finally, the third ingredient is, so that's sort of like what we're trying to get to. We're trying to get to this protocol where they do this computation by teleportation, but they could do whatever they want. So we have to force them to do that. And the way to do that is by certifying that they do what we ask. So for example, how do we know that Alice applies Bell measurements when we ask her to? Yeah. Well, so what we're going to do is we're going to sort of play half CHSH games. So we're going to keep on asking Bob to play CHSH games, so he's none the wiser. He still has to keep on measuring the X and Z bases, depending on what we ask him to. But we'll tell Alice on the corresponding qubits to do this Bell measurement, and she could do whatever she wanted. But the point is actually that if by chance we ask Bob to measure X tensor X or Z tensor Z, so which we're asking him random X Z ZX, XX, or ZZ. But if it's one of these two possibilities, the Bell states are eigenstates of those two Pauli operators, and so the parity of his measurement results should tell us exactly, agree with Alice's measurement result here. That's the idea, and that should force Alice to actually apply a Bell measurement, because if she does something else, it won't create the right stabilizer state, and so you'll catch her. And this sounds exactly like the kinds of tricks I mentioned at the beginning that don't necessarily work. But now it does, this kind of strategy you can analyze, and it does work because we know that there's a nice tensor product structure. And so you can just apply sort of standard tomography kinds of arguments. And really, so this is how it's going to work. We mix these half CHSH games with the full CHSH games in a random position. And in a random position, we ask Alice to do a Bell measurement between two random pairs, two random qubits, and she has no idea, or Bob has no idea, and so he'll catch her if she tries to cheat, because he's still playing CHSH games. That's really the idea, to mix the games in with everything else. And it's similarly on the other side. So if we want Bob to prepare a certain resource state by applying this measurement circuit, which will collapse Alice's qubit to the resource state, we just have Alice keep on playing the CHSH games without telling her that Bob's stopped. and now you just verify that the statistics of Alice's measurement outcomes agrees with the tomographic statistics that you would expect from making these kinds of measurements of this particular quantum state. So here's sort of the picture that we do know how to analyze. Well, this is sort of, again, it's an intuitive picture. So here in red, this is the computation by teleportation part of the circuit, where Bob is being asked to prepare these resource states. Hopefully he is. Alice is being asked to prepare these, to apply these Bell measurements. Hopefully she is, between random pairs of qubits. But we also need checks on Bob. So that's this sort of golden color. So Alice is applying half CHSH games, and Bob is doing this. We have checks on Alice, this green stuff, and then we have these cases where they're both applying CHSH games. And this is not to scale. I mean, a tiny fraction of the circuit is a computation. Then you have more checks, and then you have many more CHSH games than even that. And of course, you need to randomly permute things so that they don't know what's going on. They don't know which ones are CHSH games and which ones are tomographic checks and which ones are computation by teleportation. So intuitively, I think this could plausibly work. But again, actually, I don't know how to analyze this picture, unfortunately. But what we can analyze is the following picture. So it's more, instead of mixing things up with each other, which hopefully works, we just mix the protocols fully side by side. So it's probably 1/4 we play CHSH games, with probably 1/4 we do Alice checks Bob, with probably 1/4 we do Bob checks Alice, and probably 1/4 we do full computation. And so really what that means is that if you look at this theorem, the theorem said that if we play this many CHSH games and we stop before a random block, then that next block is being played honestly. And so when I say mix between these protocols, what I mean is, in the second protocol, you play many CHSH games, and then before a random block, you stop and you start playing this protocol. Because in that random block, you know that Alice is still playing CHSH games, even if Bob's being asked to do something different now.
So, sorry, can I just clarify that? So you're going to play a bunch of blocks that are always CHSH games.
Yeah.
And then for a few selected blocks, you're going to randomly do
just one block.
Just
I'm
one
going to
block.
stop in one block, and I'm going to do all this stuff. Or I'm going to do one of these three things.
Okay. Okay.
And I don't mix anything up. So I only choose one of these three things and stop. Okay. So you only get the answer with probably 1/4 if you choose this guy.
Ben?
Yeah.
So can you show us the theorem? Okay, so could you move a little bit up? Yeah, it's down, sorry. Okay, so suppose I want to improve the theorem by replacing an approximately 1 with approximately n to some power.
Sorry, n to the?
N to some constant, n to some minus 100, for example. So where would the difficulty be?
Oh, no, I don't think there would be a difficulty. I think that would be fine, because you just make an argument that you could just repeat it a bunch of times and classically say that if, let's say it's 1/2, not n to the minus whatever. So say we try to make this 1/2. You just repeat the protocol a million times and say that so there's a probability 1/2 of passing them all, and the probability of passing them all is the probability of passing the first block times the probability of passing the second block conditioned on the first block times the probability of passing the third block conditioned on the first two. And so if overall the product of these is at least 1/2, that means most of them have to be at least 1 minus epsilon. And so there you go. So you can amplify it like that.
Right. Okay.
Yeah.
So therefore you could actually state your theorem in a stronger way, in a stronger form,
I suppose.
by saying that as long as the passing chance is non-negligible, is 1 over inverse polynomial, then your conclusion is the outcome.
Yeah, I think just by sort of classical statistics arguments like this.
All right.
Yeah. Okay, so I think I'm out of time. There's a lot of other things here. Maybe let me just finish, and if there are other questions, maybe you can just ask me other questions, because there's a lot of more technical stuff. But I think I've given you the big picture of how you can. I mean, it's really this idea that you stop them at the beginning of a random block. That's really how you get the tensor product structure, which makes it all work.
Some more questions?
It's more a comment. You can derive the brick wall construction that Joe showed using teleportation, gate by gate.
Yeah, I mean, cluster
yeah.
states and teleportation is the same
Yeah,
thing.
that's right.
Yeah.
So I think this is just one way you can make a very tidy proof. I mean, there are a lot of similarities.
Yeah, but I mean, there's really sort of fundamental reasons this proof is not tidy. It's because we don't know how to, we have to play these CHSH games, and we don't know how to mix them in a nice way because our rigidity theorem is not strong enough to allow us to mix them in. So.
What do you mean by that?
I mean, we don't know how to analyze this picture here. I only know how to analyze a case when either you play CHS games, or you do computation, or you do tomography. And maybe you could prove some. I don't know. Yeah.
And if you had a more sort of diverse zoo of rigid games to tap into, where the rigidity would say, well, here you're doing an X, and here you're doing a Z, and here you're doing also some other Hadamard or vibrate.
Oh, I suppose. I see. So you can consider the blue part, the green part, the orange part, and the red part as all some game and prove rigidity for that game. Possibly. You still have the issue. Well, the issue is partly is it a small game or a big game? Because like these blue things and green and so on, they're all just constant qubit games. But this red stuff, it all links together into a big sort of spaghetti. So you still have to mix that in somehow. Whatever theorem you stated would have to allow that part to be mixed in somehow.
So yeah, I just want to clarify the comment. Yeah, I didn't say it quite right. It's just that the way you can express one of these measurement-based quantum computation in either one way or the other, like the more one-way computation-like style versus the more interpretation style. It's a little reminiscent of how we do QKD by prepare measure and the entanglement purification physical style.
I guess.
So the way you decompose it allows you to analyze the tensor product structure a lot easier.
I don't think it makes it easier. I mean, I don't know. I mean, it's essentially a trivial correspondence between teleportation and this cluster state stuff, so it's not going to give you any technical tools.
I agree with you on that. Yeah.
Sorry.
Yeah, I think I might have missed something. I'm just wondering, like in this diagram that you can't analyze, except for the part that's actually performing the computation, that's going to have to be adaptive based on the outcomes of the measurements.
Right.
Everything else, at least conceptually, whether you had the CHS edge games happening first or second, I mean, it's all the same thing, right? Like, or at least if you consider this just one big block, whether where the CHS edge games are being played, does it matter? Like, there's no time ordering on this.
Well, there has to be a time ordering. If you want to hide this part, you're going to have a time ordering, and you're going to have to also like this when you do a Bell measurement like this, it's in the actual protocol here. It's a Bell measurement between random pairs of qubits. So you need to be able to, the qubit 1 and qubit 1,000, and be able to check that Alice is doing that.
Okay, so that they're labeled.
They're labeled, and also this protocol is adaptive too. It's necessarily adaptive because teleportation is adaptive. So there's also a time ordering from that. Like, I think. Maybe.
Are you asking about reducing the round complexity or about mixing up the different blocks in the proof?
Yeah, I mean, this is a little bit vague, but I was just sort of wondering why you can't, if you have something that's ordered that looks like this, you can't just imagine that the CHS edge games were being played first for the purposes of analyzing it.
It's quite plausible that you could, if you had the kind of theorem that was strong enough, then you might be able to do that. I mean, we do make assumptions like that. Like for example, when we analyze these tomography protocols, again, Bob's being asked to prepare resource states on random pairs of qubits, but in the analysis we say by symmetry, you might as well just assume that he's doing it in sequence: 1, 2, 3, 4, 5, 6, 7, 8. And it might be the same sort of idea as what you're saying.
So
okay.
I guess.
Yeah. Thank you.